ones that carry the forces, they're like particles of light, but they're massive. And the Higgs mechanism, the prediction of the Higgs boson, as I'll show you, is really associated with explaining that, which causes a lot of theoretical problems, but now has been quite wonderfully solved. So that's the weak force, the strong force, electromagnetism, the neutrino, the electron, and the quarks. For some reason that we have no understanding of at all, nature chose to make 2 carbon copies of those 4 particles that you need to build a universe. And I know when I look at this audience of a certain age, it's good, because if I say that in a school, then people are absolutely baffled with carbon copies, like the 70s. But you know what I mean. Carbon copies in the sense that they're identical to these 4 particles you seem to need to make a sensible universe in every way, except they're more massive. So this thing here is called a muon. It's exactly the same as an electron, like the properties, electric charge, spin, all this thing. Exactly the same, except the muon is more massive than the electron. And then there's another one, the tau. Neutrinos have partners as well. The down quark was the strange and the bottom quark, and the up quark was the charm and the top quark. So there's a pattern of these 2 copies. There's 3 families of particles, if you like, and nobody knows why there are 3. We have good experimental evidence that there aren't any more, but it's one of the great mysteries of physics. Why would you have 3 copies? Not known, all been discovered experimentally. So, what I thought I would do is talk, I just want to make a little diversion and talk about Higgs, but I just wanted to mention something about the evolution, the origin and evolution of the universe, which feeds into the Large Hadron Collider. This is kind of a schematic view of the origin and evolution of the universe. It began at the Big Bang, 13.798 plus or minus 0.035 billion years ago. Good measurement, very high precision measurement. Began in a very hot and dense state and has been expanding and cooling ever since. And today, it's a universe, of course, that's full of complexity, not only stars and galaxies and planets, but things as complex as you and me, human beings. Properties of an old and cold universe. What we discovered, really, over the last century, is that as you wind time back, you imagine going backwards in time towards the Big Bang, the universe shrinks, and it gets hotter and denser and simpler. And what we find is that if you go back to the first billion seconds after the Big Bang or so, the laws of physics, the simple laws of nature, are made manifest, they're understandable. If you can recreate those conditions experimentally, which we can do with particle accelerators, then you sort of see the underlying simplicity of the universe. And the picture is that over the time that it's expanded and cooled, complexity is sort of crystallized out and obscured that underlying simplicity. One of the main steps, actually, the key moments, can be, I'm going to show 2 graphs, not too many graphs, but I want to show you this one, because you're a nuclear physics audience. And it's a graph of one of the first steps in that complexity, which is nuclear physics that dominated the universe between 10 seconds after the Big Bang and something like 1,000 seconds after the Big Bang. So we're looking back to 10 seconds after the beginning of the universe. And what this graph shows is the building up of the lightest elements, the lightest nuclei. So you start with hydrogen, you start with protons and neutrons, basically, which crystallise out around a second after the Big Bang or so. Before that, you've got free quarks and free gluons. And the universe cools enough for the protons and neutrons to form. And then what happens is the universe cools enough for them to begin to interact together through the action of the strong force. So what you see is that by 100 seconds, you start, this line here is H2, so deuterium, and then you see helium-3 switching on, and you've got hydrogen-3 there, so, and then you've got the beryllium coming up and lithium coming up. So the lightest elements that are forming up to about 1,000 seconds or so, a few minutes after the Big Bang, and then they fade away. What's interesting is that this is the theoretical prediction. We understand nuclear physics very well. We've got essentially a fusion reactor, the whole universe is like a fusion reactor at that time. But we can also measure these abundances by looking at the most distant objects in the universe. So those distant galaxies and distant stars, 13 billion light years away or so. And you find that the predictions and the experiment matches up absolutely beautifully. So this is called Big Bang nucleosynthesis. Results, roughly speaking, in a universe that's about 75% hydrogen, 25% helium, which is basically what it is today, with the heavier elements added through the life cycles of stars, and then some lithium and some beryllium. But you see that. You also see here, by the way, you see the line of the neutrons. The neutrons decaying away, because the neutrons that were made in an equilibrium in the first few seconds after the Big Bang obviously have a half-life of 700 seconds or so, and so they start disappearing unless they get captured into helium nuclei. So I think it's a fascinating thing to show, because it shows that we understand not only nuclear physics today, but the nuclear physics of the universe between the first 10, let's say, 1,000 seconds after the Big Bang, which formed the light elements. So that's the summary of the building blocks and a bit of the origin of the lighter elements. Ernest Rutherford, who discovered the atomic nucleus in Manchester, just down the road, said once that all science is either physics or stamp collecting. But he got the Nobel Prize for Chemistry saying that. Annoying him. But what he meant, he wasn't trying to insult, I think, the rest of science. What he meant was that what I've done there, and what we've done experimentally over in the 20th century, this is a 20th century construct, apart from this thing, the Higgs particle, is we discovered the particles and we put them into a pattern. But in order to do science, really, what you need is you need to have an underlying theory. You need some underpinning, some understanding of how these particles interact and why. You need the Newton's laws, if you like, of particle physics. And we have them. It's one of the great scientific achievements of the 20th century. It's called a standard model of particle physics. And you can write down the equation, the mathematics, in one line or 4 lines, and it's that. And depending on your point of view, that's either tremendously simple or a complete mess. But what's impressive about it, though, is that it summarises or encodes everything we know about physics at the most fundamental level, other than gravity. So electromagnetism is a weak and strong force, and all the particles of matter are represented in here. Maxwell's equations are the quantum version of it that describe electromagnetism. They're in here. Radioactive beta decay, the semi-incredible nuclear, the binding energy formula, all those things. Everything we know about the subatomic world and the nucleus is contained in these 4 lines of equations. And what I propose to do also, the bottom 2 lines here, are the prediction of the Higgs particle, which I'll show you, as you know, is subsequently been shown to be true. So this is the point where I ask you, you have to say the geeky version, don't you? You want the full-on, both barrels physics. It's one slide. It'll take about 5 minutes. But what I want to do is I want to just try and get an idea of how that was built up. Because the thing is, there's an essay, a very famous essay by a physicist called Eugene Wigner, called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. And the word there is unreasonable. It's genuinely unreasonable, shocking and beautiful that mathematics can be a guide to reality. And this is the best example I know, because it's a mathematical construct, really, based on experiment that makes a prediction for a new particle because of the beauty, essentially a belief in the beauty of mathematics, the Higgs boson, which turns out to be correct. It turns out to be a real property of the real physical universe. And I reckon in about 5 minutes I can give you a sense of that. So I'm going to have a go and see if it fails horribly. You can tell me afterwards. I'll see if you fall asleep. But so this is you see that this L, it's called a Lagrangian. You see this L there. So basically these form the equations of motion. If you're an engineer or a physicist, you'll get equations of motion in a system. Lagrangians will give you that just through some other equations. The system sort of turn the handle basically. This is a Lagrangian which describes a system of non-interacting particles. It's the dullest physical system you can write down in this language. It's basically, you could say electrons. So you can say this equation describes electrons with no force of electromagnetism, they just sit there doing nothing. And then this bit here describes the kinetic energy of the underground. And this bit here, which is going to be important actually, is a mass term. That m squared there is the mass of the particles. So anything that looks like that is describing a particle with mass. It can be important. Now, this formalism is based on 4 of the great pillars of theoretical physics. It's based on relativity, particularly special relativity from 1905. It's based on quantum theory, again, in the turn of the 20th century. And it's based on 2 ideas called symmetries, so the idea of symmetry and the idea of symmetry breaking. Those things are fundamental to our understanding of theoretical physics. So let me just expand that and show you how you build this thing and how you predict a Higgs particle. So this thing here, this phi, that represents what's called a field, a quantum field. So in quantum field theory, our best theory of particles are not described as point-like things that move around. They're described by fields. So a simple example of a field will be the temperature in this room. So every point in the room, you put a number. And you put 20 degrees over there, and 19 there, and 18 here, and 20 there. Imagine this three-dimensional array of numbers in the room.